Right, so let's take a quick look at what we've been discussing in the past. Last week, we talked about the vanishing gradient problem. We also talked about residual networks. And we talked about the shortcut branch in that. So now let's talk a little bit about homework number 4. Okay. Now in the homework number 4, so far we haven't actually looked at, besides Jeff Heaton's online assignments where I've asked you to look at the code and to run it. We haven't really talked about how do you actually use Keras and TensorFlow to make neural networks, right? We looked at this particular example, which was online from this particular site. And let's take a look, a very brief look at how you have hopefully been already used to running TensorFlow and Keras to actually create neural networks. So let's take a brief look at that. Let me see if I can get this down at the bottom. Okay, so you saw 2 examples of neural networks in module 3.2, okay, which you must have done some time back. So the first example was that of a regression example, and it used the miles per gallon example from the example from Jeff Heaton. Basically, what you did was you looked at a data set, which was basically data from cars, okay? There were about 398 rows in that. And there was a bunch of inputs. You had X data over there, and then you had your Y data, which was basically your prediction, and you were trying to do a prediction of the miles per gallon based on the input. Okay, so I hope you remember that. And there was various input data which was given, the weight of the car, the cylinder, the year, the origin, and so on. Okay, this was of course a descriptive data which wasn't really used. And so this was an example of regression. It wasn't classification. So the output, so the network looked like this. You had imported the sequential module of Keras. Okay, sequential basically means that you had a bunch of inputs and hidden layers, and these were all in sequence. Okay, so the input of the X input was fed into the first hidden layer and so on. Okay, it was also a dense layer. Okay, so you saw the dense layer. Dense layer meant basically that all the inputs were connected to every subsequent layer. Okay, and there was certain activation. So can somebody tell me what was the number of inputs over here? Do you recall? Number of attributes, which were how many roughly? There were about 10 inputs. Well, it was actually less than that. I think it was something like 7. Okay. So if you look at there was a weight, there was a shape, there was year, origin, there was something like 7 inputs, I recall. Okay. So there were 7 inputs. Okay. So the X dot shape 1 was basically 7. All right. X dot shape 0 would be how many? That would be the number of rows in the X matrix. Okay, X 1 would be the number of columns and 0 would be the number of rows. Right. So the number of rows would be how many? 398. Okay, and the number of columns, the attributes were about 7. Okay, so the input being given to this network was an input of size 7, and so this is X, let's say X0 से लेकर के X6 तक 7 inputs. How many neurons in the first hidden layer? 25. Okay, that's because 20. This is being specified as the number of outputs. All right, so you had 1 से लेकर के 25 तक over here. And then in the activation was based on ReLU and not sigmoid. The number of neurons in the second hidden layer would be, right? So that's 10 over here. That's given from this. And then what's the final output? How many outputs in the output layer? Just one. And why do you think there's only one? It's regression and not classification. Okay, so if it was classification, if you're trying to classify one of three outputs, you would have three outputs. Okay, so this is only y sub I, and so the loss was what we typically calculate as the mean squared error. So the loss j was equal to summation of y hat sub I minus y sub I, the whole squared. Okay, that's a mean, so you would have over 1 upon n depending on the number of n's. N was going from what se lekar ke 397, 98. Okay, from 0. So you have n is equal to 398. So this is the typical the loss equation that we're already familiar with, right? However, in the next example that you saw, which was the iris example, which was a classification example, you had the inputs. Okay, so the inputs were x sub I over here. You had about 150 input rows. Okay, and for each input row, you had the size of the sepals, the length and the width, and the size of the petals, length and width. All right, and the idea was to be able to predict which class it's going to be. And there were how many classes? One of three. Okay, so there was setosa, iris setosa, so there was another one which was vesicolor, and then there was virginica. These were three classes, all right, of flowers. And so the output was, so the input had, how many inputs were there? What would be size of the number of neurons in the input layer? 4, because you have 4 over here, right? So this was 1 of 4. What would be the size of the first hidden layer is given from here, which is 50. The size of the next hidden layer is 25. And then the final output is, how many outputs are there? Is going to be given by the shape, the number of columns in the y output. Okay. Now y was constructed using something called one hot encoding, right? What does one hot encoding do? So remember over here, the output y is 1 of 3. So you could say that iris is type 0. This is the middle one is type 1, and the third one is of type 2. All right. So there are basically 3 types of outputs, and you have to classify each flower into one of these. All right. So what does one hot encoding do? Anybody remember? Right. So if you have 3 types, you're going to have 3 columns, and you're going to say, well, if it's of type 1, if this particular row is of type 1, we're going to specify a 1 over here. If the next one is of type 2, of type 1, sorry, type 0, it will be 1 over here. If the next one is of type 1, you'll put a 1 over here. The other 2 will be 0. So there'll only be 1 for every row. Okay. And the rest of them will be 0. And if it's of type 2, you would encode it like this. Okay. So this is something called one hot encoding. Okay. So for every column, for every row, you'll only classify it into one of these possible outputs. Okay. So the output is of type shape 1. So how many would that be? So you'd have 3 outputs. Okay. And so you need to classify these, and the output type over here, the activation type over here is going to be softmax, which you've already studied, right? So this is softmax. Now there's something that we haven't studied is the loss, okay? So the loss over here is not going to be mean square error, okay? The loss over here being used is something called categorical cross entropy, okay? So what is categorical cross entropy? Now, there's a fair amount of theory behind this, and I'm not going to spend too much time in trying to understand. I've done this in the past. I've tried to explain what entropy is and what cross entropy is, and then what's categorical cross entropy. And I've realized that it doesn't add too much value. So I'm going to tell you what the equation is and try to see how it compares with, let's say, mean square error. Okay. So let's say these are the equations. Let's say you have two examples. You have a category cat and a dog. All right. You've got two inputs, and you get a particular output which says that there's an 80% chance that it's a dog, and there's a 20% chance that it's a cat. Okay. So if you do a mean squared error, what would it be? It would simply be 0 minus 0.2, that's 0.2 squared, and 1 minus 0.8, that's 0.2 squared again. So that would give you a 0.08, 0.04 plus 0.04, 0.08. Okay. Now, cross entropy basically says that we're going to use a slightly different equation. Okay. What it says is that I'm going to take the log of y sub I. Okay. I'm going to take these logs, and I'm going to multiply each one of these by the expected value. Okay. So in this particular example, what are we going to do? You're going to say that we're going to take y I hat, which is for the first case is going to be 0 times, and this is going to be natural log. Okay. Natural log of what? Of 0.2. Okay. That's the prediction. And there's going to be a negative over here. So it's going to be because all of these natural logs are going to be negative because they're going to be less than 1. Okay. And so we want to convert it into a positive number. So we're going to take this. And then what's the next part over here? We're going to take 1 over here, which is y. What is the predicted? What is the expected value? We're going to take 1 multiplied by ln of natural log of 0.8. Okay. And we're going to sum these up. Now, because this is one hot encoded, the outputs are only going to be one in one of these. Okay. Because it's a classification example. So only one of these is going to be a 1. The rest of them are going to be zeros. Okay. So you can forget about the rest of them. Suppose there are 10 categories. 9 of them are all going to be multiplied by a 0. All right. And you're only going to multiply one of them with a non-zero value, which is going to be the one that you're expecting. Okay. And so basically what you're going to end up with is the predicted value multiplied by 1. Okay. So in this particular case, you get something like a natural log of 0.8 is 0.223. Okay. So why are we doing this? Well, you could use mean squared error. It's not like you can't use mean squared error for this, but it's been shown mathematically that if you use this particular equation, which is based on cross entropy, then you get a much better result. Okay. And let's try to see what's the difference between a mean squared error and a cross entropy. So I've plotted some of these for you. Okay. So over here, I'm showing you the same example where you have a cat and a dog, and the same example, 0.8 over here, and cross entropy gives you a 0.223. We've just shown you that a mean squared error gives you a 0.08, and the cross entropy gives you a 0.223. Okay. Now I'm plotting this both on the linear scale over here and a log scale. Okay. The log scale is a little bit more useful to see. So if you look at this on the horizontal axis, I'm specifying this particular value over here. Okay, because this is the only value that counts, 0.8. The rest of them are going to be multiplied by 0, as we've already seen. Okay, so I'm plotting the value of the predicted value for the right category. Okay, and let's say we call that whatever we've called it over here. We've referred to that as yi. So I'm plotting yi for the value which was the correct, that corresponded to the correct classification. Okay. So in this particular case where yi was 0.8, what did we see? We saw that the mean squared error was over here, which was about 0.08. Okay, this particular value. And the cross entropy was a little higher, was 0.223. Okay, so you see these 2 points. You see that the mean squared error is giving you a lower value, and the cross entropy is giving you a higher value. Okay, Now, if you plot the entire scale, what you see is that generally where the values of p become of y sub I become extremely small, okay, somewhere over here. So you have a very big inaccuracy. In other words, you're predicting, let's say, a 1% chance of, let's say, a dog, whereas in fact it was supposed to be 100%, right? So the mean squared error would give you a value of something around here, okay? It would give you a maximum value of 2. But the cross entropy would give you a much larger value, okay? So it would keep on going larger and larger. So you can see over here that it's basically what it's trying to do is that if you have a very inaccurate answer, then it's going to give you a large value over here, okay? So it's going to give you a large value of the loss, okay? So it has certain advantages, okay? Over here, you can see that in the log scale, these two also start to differentiate. So it's basically able to differentiate. The mean squared error sort of clumps up the results, okay? And especially over here, it is not able to give you large losses where in fact it should be, okay? So that's one of the advantages of having a cross entropy. But again, as I'm saying, I'm not explaining you a lot of the mathematics behind it, and if necessary, we'll go into that. Okay. This is another example, and I've shown you. There's a nice YouTube video if you want to look at this, which is given over here. It actually explains the whole process in much more detail. It gives you an example of a multi-class classification, right? So here you have an example where you've got 8 categories, right? And let's say you're predicting a cat. The correct prediction is that this is, I don't know what a red panda is, but they've given an example of a red panda over here. So the red panda was predicted to be 25%. Okay, so this was your prediction for the red panda. Okay, so what did you do for the cross entropy? Basically, what you did was you multiplied all the rest of them with a 0. Okay, because all of the labels here were 0. So the only thing that was of interest was that you took the summation of p sub I times log of q sub I. They've called it p and q over here. P is the label and q is the prediction. You can have these different variables. So you've got to be familiar with these when you look it up, when you look at some of these online, or if you look at them in books, you'll often have these different variables over here. So eventually, all of them drop out. The only one which comes in.
Red Panda is what the Firefox browser is named after.
There's a question online. Is there? Just hold on a second and I'll come to you. So basically what you do is P over here is going to be 1. Okay. So this is going to be a 1. It's going to be multiplied by the log of the predicted value 25%. And that's how you're going to get this. So is there a question online?
Yeah, sir, I was just saying that red panda is what the Firefox browser is named after. That's the animal.
So I'm having a difficulty hearing you. Let me see if my audio is too low.
Yeah, can you hear me now?
Well, I'll try to hear you. Yeah, just speak up a little.
Yeah, it's not a question. I was just saying that red panda is what Firefox browser is named after. It's the Firefox animal. Yeah.
Okay, that's information for me. So Firefox has been named after red panda. Just some interesting tidbit. Okay, thanks for that. So so this is an example of cross entropy where it's being applied to multiple classes, not just the 2 classes that I gave you a simple example of. Okay. So that's as far as the example of how to use when you're doing classification examples. You'll generally use categorical cross entropy. If you're using regression, you'll use the previous one. You'll use a different loss for mean squared error. If you have, by the way, if you have only one of 2, instead of using categorical cross entropy, you often will see that they use binary cross entropy. Okay, so that seems to be kind of obvious. Okay, so if, for example, in the homework, If you search online for the kinds of solutions that I've encouraged you to do that, although I'm not saying you should try to find a solution on your own, but if you do find solutions online, you will see that they'll use binary across entropy, okay? So that explains the homework a little bit. I'm not sure if I need to go into any more details about the homework. I hope that you will work on that. Does anybody feel I need to go a little bit more about into more details about the homework? Ji. So मैंने आपको जो example homework number 4. So let me just show you the homework. Basically, what I'm asking you to do is, and this is really for your own learning. A lot of times you just use a data set which is available, okay? You don't really realize what are the issues in creating your own data set, okay? So I've asked you to create possibly X's and O's, okay? So what you can do is go into Paint and just create your own X's and O's, okay? You'll see that when you use that, you could have actually different image sizes. You'll get into all kinds of issues, okay? So, and you need to create 20 of each, okay? You can use different brushes and so on. You can use different styles. So this is sort of relates to the example that we've already done, okay? Alternatively, if you don't want to do that, what you could do is I've worked with both of these examples. I took a couple of my grandkids and I classified them. I took pictures of those, and when you're cropping them, each one of them will be of different sizes. Okay, so that's also an example. When you're creating your own images, you'll find all kinds of issues when you create these. So you could do that. I don't want you to take anything from an existing data set because then you're not learning how to create your own data set. It should be balanced. In other words, the number of X's and the number of O's should be the same, okay? It doesn't have to be X's or O's. You could also say, for example, you create a bunch of X's and the others could be all the other alphabets. It could be 1, 0 se lekar ke 9 tak, okay? That's a better categorization. That's more robust. Yeah. Yes, I want you to keep it simple. In this particular case, just keep it binary. Okay, so you're classifying 1 of 2. If you want to challenge yourself, you can do it beyond that, but that's not what I'm asking you. Okay? Ji. Kiska? AlexNet, right. So I'm not asking you to use some major existing network. I'm asking you to create your own simple version of it, okay? So I've asked you to predict, I've asked you to use 2 to 3 layers if I'm correct, yeah. So I want you to create your own network, a convolutional neural network, okay, using Keras and TensorFlow. So you can't use something else, okay? You can't use PyTorch or something else that you're maybe already familiar with. I want you to create your own neural network. It could have as many, well, 2 to 3 layers. I don't want you to go too deep, okay? How many neurons do you want? It's up to you, okay? You can experiment with some small number of neurons, see whether it works or not. Try to change the number of the size of the number of neurons in each layer, okay? And see what the results look like, okay? What else would you need to know? You would need to have some data for validation as well. Okay, so you'll have to split your data into your training data and validation data. And what I'm recommending is that 20% should be used for validation. So if you created 40 images, then for 20% of those images will randomly be selected for validation purposes. Okay. You could use other things that you've already learned. For example, you could use regularization, dropouts. If you want, it's not required. If you want, you can have overfitting could be looked at. So you could have early stopping. You could have all of that, but that's not really required. So you're just looking for a very simple vanilla kind of a neural network and try to see if you can get your results. Can you see, and try to do it different number of times, all right? So it's possible that first time around you tried, you get some excellent results. Next time you just rerun it, you may get terrible results, okay? So, you experiment with this so that you get a good feel of how the convolutional neural network works. G. Okay, just a comment. I've given you solutions for the first two homework sets. I haven't done the third one. And I've also graded them, and I've also given comments. So I hope you're seeing my comments, okay? So sometimes if you don't answer the questions, like I'm saying, discuss something, and you don't discuss it, you get points, you get negative points for that. For example, I asked you a particular value of R, what's the optimal value of R? If you're not specifying that, you'll get some points, from there. So coming back to this, so I've asked you to possibly comment. So this is where I expect you to comment, all right? So look at the results, and so if you're looking at your results and you look at the 20% cases and you find that you do an X, something like that, a random X, and didn't come out well, it was misclassified. Can you give an intuitive answer as to why it was misclassified? Or maybe you have absolutely no idea, but just think about it, all right? Think about why a particular case was misclassified. So you should be able to see which images were used for training and which were used for validation. And then based on the training, you might be able to say, okay, so the validation data image looked very different from the training data, and that's why it was misclassified, okay? So something like that. That was the question. G. Yes. So in all of this, you're going to be using a loss function. Hopefully, you're going to use the right loss function, not mean squared error. Okay, this is classification. And then you're going to see the overall loss. You're going to be able to use, as I've given you an example, that you can use model.predict. This was given in one of the examples in Jeff Eaton. You can use model.predict. You can give it a particular image, and it will give, based on your trained model, it will give you the prediction of that particular model. Okay, so for a particular image, you give it from the validation. If it gives you, a bad result, a bad accuracy, then you need to give an idea as to why is it so bad. Okay. No, so you're just creating one of them. I'm not asking you to do both. I've said or. Okay, you may create one of the following. Okay, you could use the X's or O's, or you could use your favorite images and so on, but create your own images. Okay. So, and I want you to submit your entire IP. I didn't specify that, but I want you not just to upload your Python code, but your Jupyter code, right? IP NYSB, something like that. Okay, so that I can just look at it and I can run it as well. Okay, so that was all about the homework assignment. Okay, so let's continue from where we left off onto regularization. Okay, so last time we spoke about two types of regularizations. We talked about early stopping, okay, and we talked about dropout. All right. Now, today we're going to talk about a third type of regularization, and this is called L1, L2 regularization. Okay. Now, what this does is it takes the loss equation, okay, and what it does is it adds a regularization term, which is a function of the weights. Okay. Now, what do you think by adding to the loss equation a function of the weights, what do you think this is going to do? First of all, loss को हमने maximize करना होता है, minimize करना होता है, minimize करना होता है, right? So we try to minimize this. So we normally try to minimize the error, okay? For mean squared error, it's this. For cross entropies and so on, it's different. It could be anything over here. But basically now what we're saying is we're adding something to the loss equation. So it's going to make the loss equation better or worse? Is it going to make it smaller or bigger? Let me put it this way. So we're adding some value over here. Is that, and this value hopefully presumably is a positive value. So is that going to make is it going to increase the loss or is it going to decrease the loss? It's going to increase the loss. So it's actually going to increase the loss. It's going to make the results worse. Okay. Now the question is, can you think of why we're adding a function of the weights? It could be a function, something like, summation of W sub i's. Okay, so we could have some summation of W sub i's, simply a sum of all the W sub i's, or it could be some weights of these. So for example, you could add some beta value of I. So you're doing a weighted sum of all the weights and so on. And then you're multiplying it by some constant, which is the alpha value, which is sort of the regularization constant. Okay. So now the question is, what do you think it's actually doing? And can you think of why we're doing it? Why would you want to add a function of the weights? Okay, so you're saying basically when you try to minimize this, what is it trying to do? For example, if you have this equation, what is it going to try to minimize as well? The error, so the error is over here. Okay, there's no error term over here. Is there an error term over here? There's no error term here. It's simply taking the weights and adding them up. Okay, it's taking a weighted sum of the weights. But let's keep it simple. Suppose it's simply taking a sum of all the weights. Okay. Now, sorry. It's sort of like adding a bias. Yeah. Right, right. So what we're trying to do is we're trying to minimize the value of the weights. Okay. Now, can the weights be positive and negative as well? All right, so it could be positive and negative. Now, if you're trying to minimize the weights, if you do this, you're basically trying to encourage a lot of negative weights. Okay, you could have negative 1,000,000, right? Is that good or bad? What does that mean? If you have a very large weight, let's say that you had a particular, if you look at your simple case, you had x1, x2, and this was your y, and you had your f over here, which is the sum of these two, and you had w1 and w2, right? Suppose that W1 became extremely large, all right, 10 to the power 6, and W2 was 1. What would that mean? It would, so basically, so it's, what are we doing? What about X1 versus X2? Is X2 going to be utilized over here? So essentially, this particular feature is going to be neglected as compared to this particular feature. Okay, so if the weights become very large, what could happen is that some features could be overly representative and other features may be completely neglected. Okay, and if one of the weights becomes extremely big, it's actually going to negate all the other features. Okay, so that's not necessarily good. We want to have a combination, some combination of all the important features. So that's why it's good to make sure that the weights don't become too large. Okay. So one of the things that we're doing over here, we're trying to say that the weight should be small. Okay. But by having the value Wi is a negative 10 to the power 6 going to be possible? So if this becomes negative 10 to the power 6 W1, is that going to reduce the loss? That, we're trying to reduce this whole term, right? We're trying to reduce the loss to as much as possible. So if we had W sub I over here, just a positive W sub I, then basically what are we saying? Can we have very large values of Wi? Can we have very large positive values of Wi? Large positive values of Wi are going to be discouraged because we want to reduce the whole loss. So if one of them becomes, if this is W1 plus W2, and we're trying to reduce this, is basically going to say that both of these should be small, okay? But if it's just W1 plus W2, negative large values can also be included. So this could, maybe 10 power 6 positive is going to be discouraged. But if it becomes negative 10 power 6, is going to be allowed because we're trying to reduce the loss to as low as possible, and negative losses are also acceptable. Okay, so what do we want to do over here? We want to take the absolute value. So we're going to, first of all, we're going to do is we're going to take the sum of the absolute values. Okay, and what this will simply do is make sure that the magnitude of the weights becomes small. Okay, so negative 10 power 6 is also not going to be encouraged. It's going to make sure that the values are relatively small, the absolute values. Okay, so so this is one way of actually trying to reduce large weights. Okay, now there are two types of losses. G. So G. Right. So if one of those values was becoming very large, okay, we would basically say that we're trying to minimize both of these. Okay. Now notice that what we're doing is we're going to take the sum of the absolute values. Okay. So we were going to basically say W1 plus W2 needs to be minimized. Okay. So what this means is that if either one of them becomes large, we're going to make sure that neither of them becomes large. Okay, both W1 and W2 have to be small. If one of them starts to become very large, it's going to be reduced. Okay, so ये बात सही होगी. अब आपका जो दूसरा सवाल था कि can we now use other equations? So this is one example of an equation. Okay, and this is one of the losses. This is what is called an L1 norm. Okay. We're taking the absolute values, but we could take what is also referred to as the L2 norm. So what you could do is this is simply the summation of x sub i's. Okay, the L2 norm and can be written down as, or the pth norm can be written down as x sub I, okay, to the power of p, and then take the pth root. Okay, in this particular example, it is p is equal to 2. Okay. So this is the pth norm. The second norm will look like what? It will actually be x1 squared plus x2 squared and the square root of that. Okay. So you could have all kinds of norms over here, but each one of them has a different property. Okay. So now what do you think this looks like if you plotted this? If you plotted both of these, we have x1 over here and x2 over here. Okay, or rather, sorry, these are supposed to be w's. Okay, so I'm going to rewrite these as w's over here. So this is w1 plus w sub I to the power of p. Okay, this is w1 and w2. Okay, so we're taking the sum, we're taking the weights. All right. So if you plotted w's over here, w1 and w2, and we plotted w1 and w2 over here, we plotted p is equal to 1 and p is equal to 2. What do you think this will look like? This is the sum of those two, and we want to, let's say, make this equal to 1. All right. So we're saying that the W1 plus W2 has to be equal to 1, the absolute values. So what's the equation where W1 plus W2 is equal to 1? Is there a line? Is there a is that a circle W1 plus W2 is equal to 1. How do you plot a straight line?
Sir, it would be two
Y
parallel
is equal to
lines, I
mx plus
guess.
g. Sorry.
Sir, I said two
Sorry.
parallel lines would be formed.
Parallel lines will form. Okay. So the suggestion being given is that if you have an equation which says W1 plus W2 is equal to 1, the slope is going to be positive or negative. Y is equal to mx plus c, right? So it's going to look like this. This is the equation for W1 plus W2 is equal to 1, right? Okay. Now we want to have this equation W1 absolute value plus W2 absolute value is equal to 1. So you could have this over here, but you could, and you can think about it, it will look something like this. It'll look like a diamond, okay? In other words, this particular point over here will be when W1 is equal to 0, but W2 is equal to -1. Okay, so you can see that if you plot the absolute value, this is how it's going to look like. Okay, I hope you can see that. Okay, what about the P is equal to 2? It's going to be a circle, right? So this is the simple equation for a circle. Actually, here the absolute values don't mean anything because when you square them, it automatically resolves the absolute value. So this is simply the equation of a circle with a radius of 1. Okay. What do you think P is equal to 0.5 is going to look 0.5 is going to look like? So you can see that this was when P is equal to 1. This is what P is equal to 2 is equal to look like. This P is equal to 2. P is equal to 0.5. So what happens when, well, whichever is easy. P is equal to 4 kaise hoga? Any guesses? Okay. Well, I'll show you the answer. It looks something like this. Okay. So this is where P is equal to 0.5. It's sort of, it's a convex. Okay. P is equal to 1 looks like this. We've already seen this. We've already seen this is a circle. Where P is equal to 4, this becomes W1 to the power 4 plus W2 to the power 4. It looks something like it approaches, if you have something like P is equal to infinity, what do you think it's going to look like? It's going to be an absolute square. Okay, so if you have P is equal to, as P approaches infinity, it's going to look like an absolute square. Okay. Why is that? Because for any value W1, which is slightly less than 1, it's going to become essentially 0. Okay, so the only way that you can have that is when W2 is absolutely equal to 0. If any one of these, for example, over here, either one of them is slightly less than 1, if you raise it to the power of extremely large number, it's going to become 0 because, as you multiply numbers which are smaller than 1, they becomes smaller and smaller. So you can see that it eventually approaches a square. Okay. Dimension agar बढ़ा दें, for example, this is where it's equal to 1. All right. So this is the equation where this is equal to 1. Right. Now, if you're saying K, it's equal to 2. Okay. Suppose that I want to have the equation for this is P, the summation of this is equal to 1. Right. This is that equation. What happens when this is equal to 2? What do you think it's going to look like? I'm not sure if that is your question, but let's look at this. It would be a shift which way? So clearly this equation over here, you can see that it's going to be over here. This is W1 plus W2 is equal to 2. All right, it's going to cross it at 2. It's crossing at 1. And you can imagine now that it's going to be something like this. Right? So it'll be larger, but it's going to have the same shape. Similarly, if your circle is smaller, this is going to be, if this was crossing at 1 and this is crossing at 0.5, what do you think is the equation for this? This is W1 plus W2 is F. So in other words, F is in this particular case is equal to 0.5. Okay. So this is where F is equal to 1. This is where, sorry, 2. This is where F is equal to 1 and so on. Okay. So it'll simply become larger or smaller depending on what is the absolute value. Okay. Now, let's try to understand what this particular equation is trying to do. Okay. It's trying to basically say that your original loss equation, okay, is going to be combined with another set of equations, and you're trying to minimize both of them. Okay. So let's try to visualize this. So let's say that this is your loss equation. This is loss, or you can call it J or whatever. Okay. This is your mean square error, right? We've already seen this. You've already done this in your third homework assignment, right? And you saw that your equation, you could be approaching this like this, and so on, or you could be approaching it in a straight line as you pick better and better weights. If you're doing stochastic gradient descent, this is how you're approaching it. If you're doing pure gradient descent, hopefully you're doing a more accurate, deep, approaching the optimal solution. Okay, so these are all values where is the loss L increasing or decreasing? It's, if you're going outwards, it's increasing, right? And if you're going inwards, it's decreasing. Okay, so basically what we're trying to do is we're trying to get to the center. We're trying to find the optimal values of W1. So this is plotted with W1 over here and W2 over here. Okay, we're trying to find the optimal point where you have the minimum loss, and you're trying to find the optimal values of W1. Let's call this W1 star and W2 star. Okay, this is your normal loss equation. Now, what happens when you combine it with another equation? So now we're saying that we're combining this with another equation, which is W1 plus W2. Let's say squared करने में फिर आसानी होती है. Okay, we're trying to combine this with this. Now, where does this equation fit in over here? Where should I, if I try to plot these separately? So this is, it's got a loss equation over here, the original loss equation. जो हमने यहाँ पर plot कर दिया. Okay. Now I'm trying to plot this. Where do you think this? Keep going. So I'm only trying to plot this part. Origin से ये center की तरफ इस तरह जा रही है. Okay, this is an equation of a line. We've already seen this before. We saw this, this was the equation. This was what it was, right? It was a circle, which was, where was this? Where should the circle be? Should it be over here? Where should it be? It should be over here, right? So this is the circle. If this is equal to 1, right? If this is equal to 2, it's going to be equal to this, right? So now we're trying to minimize both of these. If you're trying to minimize only this part, where is the answer to this? You're trying to minimize this. What's the answer to that? What should be the optimal values of W1 and W2 if you're trying to minimize this part? It's going to be 0 clearly, right? Because when W1 and W2 are 0, clearly the sum of those two, the square of the sum of those two is going to be 0. So that's going to be a 0 over here. This is a 0, this is a 1, this is a 2. So this is equivalent to, if you didn't have this, all right, basically if you wanted to minimize this and you started over here, you'd basically go in this direction, right? If this was the only part of the loss equation. But now we've got two parts in the loss equation. We've got one part which is a series of concentric circles. And we've got another one, which is maybe non-concentric circles. And it's centered around some other place. Okay, it's not centered around, we already know this. Optimal weights are not necessarily at 0. Okay, but this here equation is trying to minimize them. It's trying to say I'm going to optimal solution is when the weights are the smallest, where they're 0. The other one is saying that the optimal solution is over here. Okay, so this is one optimal solution. This is another optimal solution where, and you're trying to have some kind of a combination of those two. And the combination is weighted by the value of alpha over here. Okay, if you remember what I'd written over here, there was a value which was a constant, which was given, which was multiplied by the second part of the loss equation. Okay. So now when you're combining these two, let's say we're trying to combine these two, where do you think the optimal solution will be? So let's say the center, will it be somewhere over here? But this is saying that the weights, the sum over here is very large, because the circle that's going to go around this may be, you know, this is 0, 1, 2, this may be 20, all right? This could be that the sum of these, the x1 squared plus x2 squared, square root of this is equal to 20, right? So let's say the optimal solution W1 and W2 are the original optimal solution was where this is 3 and this is equal to 3. So this is going to be a 9 over here. Is that right? 18, square root of 18 actually. So it would be 3 squared plus 3 squared, that's 9 plus 9, 18. This is going to be square root of 18. Okay, so something 4 point something. So this is going to be, let's say 4 point something, 4.2 for example. Now, the other part of this equation is trying to minimize the W values. Okay, so do you think the optimal solution is still going to be over here? What if alpha value, the constant over here that we're multiplying is really large? Let's say alpha is equal to 10 to the power 10. Where do you think the solution is going to be? Is going to be near the origin, right? Because as soon as this becomes slightly bigger, this number here is going to multiply with such a large number that it's going to force the solution to be somewhere close to here. Okay. What if alpha was really small? So alpha was, let's say, a 0.0001. Where do you think the solution is going to be there? It's going to be over here. Let's call this a 0.0 and this is point x, right? So it's going to be closer to x or 0? It's going to be closer to x because alpha is so small that there is no weightage over here. Okay, so it's going to be very close to this. So depending on the value of alpha, if you make alpha very large, it's going to force the weights to be very small, and the solution is going to be closer to the 0. If you make the value of alpha very large, then it's going to accept large weights. Sorry, if you make the value of alpha very small, it's going to accept very large weights and is going to be closer to x. If you make the value of alpha extremely large, then it's going to be closer to, it's going to make the weights very small. Even though the optimal weights are large, it's going to make the weights very small. Okay. Now the question is, what about the ratio of alpha of W1 to W2? Okay. So suppose that alpha is some reasonable number. Alpha is equal to 1. Okay. Not too small, not too large. Okay. Now, if you look at this particular equation over here, all right, if you look at the original stuff, you can see that the original value, the original equation over here is not exactly, it's not really saying that W1 and W2 are not really equal, are they? Can you tell me which one is going to be larger? W2 is probably going to be larger. So let's assume that this is 5 and W1 is 4, okay, as an example, okay? So basically what we're saying is that the optimal solution is if alpha was extremely small, it would be W1 is equal to 4 and W2 is equal to 5. This is going to be the optimal solution. Okay. Now, however, and this is where the circle is going like this, right? Now, suppose that alpha becomes slightly larger and we pick a circle which is over here. Okay, so these are larger and larger circles. Okay, where do you think the solution is going to be? It's going to be somewhere. Can I convince you that it's going to be somewhere along this arc? As it goes to 0, between these 2 points x and 0 is going to be the points where these circles are going to intersect. In other words, you're not going to find a solution over here, okay? Because here these circles are concentric. They're weighting W1 and W2 equally, all right? So it's going to pick a value which sort of looks somewhere where at the intersection of a circle and these original contours, okay? And if you don't completely get that, think about it a little bit more, and perhaps you'll be able to get this, okay? G. So, okay, so we're not saying what should be the size of alpha. We're saying, let's say we're given a certain alpha value, okay, somewhere from out of a box, all right, out of a black box. We've just got some value, and we're working with some value. So now, depending on the value of alpha, suppose that we're taking a value of alpha is equal to 1. For that particular value, all I'm trying to say is that the solution that's going to be found is going to be along this particular arc, okay? And you can see why I'm getting this arc is because these are the points where the circle, the concentric circles, are going to have their tangents, the tangent of the circle and the tangent of these two are going to meet. Okay, this is a little bit, it's a bit hard to see, but I'll show you an example of this. Okay, so here's the bunch of circles. Okay, here's a circle. And here are 2 examples. So this is where P is equal to 0.5. And here, this is where P is equal to 2, right? So both of them, in both of these cases, you've got these two, concentric images, okay? And let's take the case where P is equal to 2 first, okay? So when P is equal to 2, as I said, you're going to have the original solution is probably going to lie around this particular arc. As it becomes larger and larger, it's going to eventually come over here, but it's probably going to be at the intersection of these 2 points. Okay, I'm not explaining it very mathematically, but just to give you an intuitive idea, okay? Now, what happens when P is equal to 0.5? Now, can you imagine that, and this is what the argument that I'm making, is that when P is equal to 0.5, you are most likely going to end up with one of these W1 or W2 values are going to be equal to a 0, either W1 or W2 is going to be equal to a 0 for P is equal to 0.5. And the argument that I'm making is that for P is equal to 2, this optimal solution is not necessarily going to be where W1 and W2 are equal to 0. Okay, in this particular case, they're going to be greater than or equal to 0, or probably greater than 0. So let's say you find the optimal solution over here. Okay, let's say this is point A and this is point B. Okay, Can people see why the solution for p is equal to 2 is probably going to be where these are not necessarily 0, but where p is equal to 0.2 because of the structure, because it's concave, as the circle, as these become bigger and bigger, is going to intersect with either it over here or it's going to intersect over here, depending on where it is. So for example, you had these concentric circles somewhere over here, all right? It's probably going to end up intersecting this point over here, okay? Can people see that? Basically, what I'm trying to say is that when p is equal to 0.5, the optimal solution is going to be where one of the weights is going to be equal to 0. It's concave. So as this becomes bigger and bigger, it's going to find a solution where one of these that is going to be on the edges, okay? Because those points are going to be appearing first as that concentric circle becomes bigger and bigger, okay? So if you can see that, then you can see this particular argument that I've written over here is that for p is equal to 2, okay, the point A is going to be where W1 and W2 are not necessarily 0, but for p is equal to 0.5, you're going to have one of these two equal to 0. That's where the optimal solution is going to be, okay? And if you're convinced of that, what does this imply? What is this saying in terms of the number of weights? So basically what we're saying is that you're going to have an optimal solution, and when p is equal to 0.5, one of these two are going to be equal to 0, okay? So what has this done to the number of features? एक feature reduce हो गया, एक feature का आपने, in other words, आपका जो original था, it was something like this, x1 and x2, this was w1 and w2. Now by saying that one of these is equal to 0, what we've said is that one of the weights, one of the features is going to now become unimportant for the final result, okay? So what this is doing is that it's basically reducing the number of features, okay? By taking a value of p which is less than 2, which and if you can see over here, in general, if you have p is equal to 1 as well, p is equal to 1, this is also going to have, and this is not so obvious, but this is also going to have a similar kind of effect, not as much, but it's going to have similar kind of effect that is going to try to reduce one of these to be equal to 0, okay? But the smaller the p, the value that you pick, the larger the chances are that one of them is going to be a 0, okay? So if you want to reduce, in other words, if you want to have a sparse solution, okay, you've got, let's say you've got an extremely large neural network, all right, with let's say 10 to the power 3 weights, okay? As you know, we can have weights are parameters. You can have extremely large number of parameters, but you want to only focus on the important parameters. Now, let's say that one of those parameters is unnecessary. You've already seen that. On the playground, you saw that if we keep on adding a lot of additional parameters, it doesn't necessarily help, okay? And even in the examples that we've seen, that if you have a large number of features, it doesn't always help. If you're trying to figure out between X's and O's, we saw that optimally you just need 7 features, okay? But let's say you start off with 100 features. Only 7 of those were important. The rest of them were unimportant. So by picking a regularization and let's say an L1 as opposed to L2, will L2 have the same result? So L2 was where this was, it was the circles, right? This was called the L2 regularization. L1 is where you're taking the absolute value, okay? So if you take at L1 and L2, these are, by the way, they have proper names. This is called lasso, this is called ridge, simply because these are the two most popular L1 and L2 algorithms that are used. So which one would you want to use if you want to have a sparse solution? In other words, you want to have a reduced number of weights. You would want to use L1. And if you don't really care about the sparsity, you just want to make sure that the weights are not very big, then which one would you use? You could use actually both of them. You could use L1 or L2. If you simply want to reduce the value of the weights, you probably want to use L2. Okay, but you could also use L1. L2, what it does is it's it's almost the same because it's the square root of the squares. So so getting back to the original idea is that if you wanted to reduce if you wanted to reduce the weight values, okay, if you wanted to make sure that the weights don't become too big, you could pick either L1 or L2, okay? The bigger the value of alpha, the more importance you're giving to it, okay? So if you, by picking a very large value of alpha, what are you going to get if you're taking, let's say, an L1 with a very large value of alpha? You're probably going to have a very sparse network because remember, this is only in 2 dimensions, W1 and W2. What if you have 3 dimensions? Okay, then you can imagine this is going to be a real diamond, you know, in three dimensions. 4th dimension, we can't even envisage it, right? If you have a million dimensions, which would happen, if you have a million parameters. Remember that I talked about GPT-3, which is an NLP algorithm, which is becoming very popular. That has how many parameters? Does anybody remember how many I said? 175 billion. Okay, so what are the dimensions of this? This is 175 billionth dimension. Okay, you can't even imagine what it looks like. So if you're trying to you're trying to make the complexity of the algorithm, then you would want to have an alpha which is relatively large. Okay, you would want to have a p-value. If you want to have really small, you want to have very sparse network. In other words, instead of using 175 billion parameters, all you wanted was 1/10 of that or 1/1,000,000th of that. You would probably want to put. How would you want to pick p? Would you pick p to be 2? You would probably pick p to be 0.5, right? You could pick it even smaller. You could probably pick it 0.1 as well. Okay, the smaller that you pick it, the more sparse, you would be reducing these 175 billion parameters, and you're only taking the important ones. Okay, so this is a completely different type of regularization, which we saw as compared to the earlier ones. How would you compare this with the other 2 regularizations that we saw? Okay, so we saw early stopping, we saw dropout, and we saw L1, L2. So can you do a rough comparison? Are they overlapping in terms of what they're trying to achieve? Are they completely addressing different issues? So let's look at it again. What is early stopping looking at? So it's trying to stop overfitting, okay? And what is dropout trying to achieve? Yeah, so what do you think dropout is trying to achieve? Well, not really, because remember, they're going to be dropped out for one epoch, and then the next epoch, they're going to come back. Every epoch, every iteration, or every batch iteration, they're going to be dropped out and they're going to come back. So how does this compare with? All of these are somewhat like overfitting, absolutely right. But what is dropout doing as compared to early stopping? So dropout is essentially trying to say that if one of those neurons is becoming too important, it's sort of like overfitting, and its weight was becoming essentially too big. Okay, that's what it would mean. That is going to be reduced by randomly dropping these. So it's going to try to use all the neurons, in a weighted manner. So they're not exactly different, and they're somewhat similar. And how is this doing the same kind of thing? Yeah, so by making sure that the weights don't become too big, it's also making sure that there is not too much reliance on a particular neuron, okay? And it's also doing, so what about sparsity? Is that being done in any one of these two? Not much or not at all? Is either one of these, is early stopping or dropout addressing the issue of sparsity? In other words, is it trying to enforce that some of these weights are going to become zero? That's not happening at all, okay? So this is a unique aspect of L1 regularization, not L2, but L1, that it's ensuring sparsity as well, that some of the weights are going to become zero. Okay. So that's as much as what we're going to talk about regularization. And let's stop over here, take a 15-minute break, and then we'll come back to our next topic, which is now going to be a completely different architecture. Okay.